Good afternoon all. Now we'll start with the body plot, right? And we'll see how this body plot can be plotted and how you can comment on the stability using the body plot. Just a minute. Yeah. So, body plot. Now one thing is clear, body plot means again it is related to the frequency response analysis. We had seen polar plot, we had seen Nyquist plot, right? And out of all these three you will find yes, best is what is the body plot. Now why? Just when you'll understand the basics of that, you'll come to know that plotting a body plot is very simple and extracting result also not that easy compared with the, not that direct compared with the this thing root locus, but definitely if you'll compare with other methods that are coming under frequency response analysis, you will find body plot is simple one. Now why it is simple one, right? We'll try to talk about that first. Just a minute. Yeah, so first point, we'll talk about the basics of the body plot. If you see polar plot, right, we had seen that too many calculations are there. That is not the case with body plot. You will find, because some more things that is done by body, including the Nyquist, right? You will find plotting will be with less calculations. Previously you have to study for the, or you have to get all those things which are related to the body plot. The back material will be ready with you, and then drawing the body plot will become very simple. So Bode used basic idea of Nyquist only. Now what was the basic idea of Nyquist? It was magnitude plot and phase plot, right? You were drawing them together. Now you will find, yes, again the basic idea is plotting magnitude and phase. Yes, but we are going to draw them separately now. So these are also magnitude and phase plots. The basic idea is same. He added something to that. So what are the things that he has added? Okay, I'll write over here first thing, that is all these are basics. Point number 1, or I'll say point number A, and that is basics we are trying to see for body plot. Yeah. So let us say you are having a simple transfer function. एक example लेते हैं, GHJ omega is equal to K J omega plus 1 J omega plus 2. Correct? Now when we are talking about Nyquist plot, you might have seen that yes, we have to divide. These are in multiplication or multiplicative terms. These are, or you can say yes, division is there, right? Now Bode took log from both the sides. And because of that, you will find that this multiplicative terms become additive. Terms become additive, and as soon as it becomes addition, it becomes easy to go for. The multiplication will be addition and your division will become subtraction, and then because of that you will find it becomes easy to plot. So the individual components, and one more thing, this is one thing which is happening. Second thing, because you are taking the log, you will find that the individual components, they are becoming straight lines. So I'll write in short, individual components, they become straight line. Now how they are becoming straight line, yes, we'll see. ठीक है. And now n number of components, like this is a straight line, this is a straight line, all are straight line. Because you are taking log, they will become straight line, and then adding all these straight lines, it becomes comparatively easy. If you are having some curves and if you want to add them, then it becomes difficult, right? But if you are having straight lines, adding them becomes very easy. Just at looking at the graph, you will be able to make out ki how the addition will be there, right? So I'll write one more thing, addition of straight line is simple or easy. Is easier compared with the curves, right? If you are having curve as the overall thing. So that means one thing is fixed, that now more stress on the log part. So definitely you have to take the log. So before that, we'll try to split this thing into magnitude and angle, just say always we used to do, and then we'll think of, if we'll take log, then what is going to happen. So if I'm talking about magnitude of this, then the magnitude will be k over here under root omega square plus 1 divided by, yes, omega, and the second term will be under root omega square plus 4. So now this is the magnitude. And if you are talking about the angle, let me separate this. Angle of GHJ omega. Yes, then very well you can write this is K, so no angle is there. For this it will be tan inverse of omega. Remaining two terms are in the denominator, these are poles. For this j omega, angle is going to be minus 90, upar gaya, so it is minus 90. In the denominator it was plus 90 in the positive direction of y-axis, correct? This component is also in the denominator, so it will become tan inverse of omega by 2, correct? So this is angle. Now see, very well it is understood. Over here it's linear only, so no need to take log for this. So even if I'm saying yes, we were Bode plot means what, you are taking log over here, no need to talk about log of this, only log of the magnitude. Even if you are taking, that is going to solve the purpose. That means log only for magnitude. And see, whatever points I'm telling you now, if you'll add them all, then you will find, yes, the idea of Bode plot will be more clear. Now you just keep on understanding one point whatever I'm trying to tell you. So if I'll take log for this magnitude, I'm going to have log of magnitude of GHJ omega is equal to log of k. Now multiplication, so it will be plus log of omega square plus 1 minus log of omega minus log of under root omega square plus 4. Okay, fine. So we have done it for the magnitude part. Now the unit of this logarithmic term or the magnitudes that we are going to have, the unit is decibel. I'll write unit of gain is decibel. We used to denote it by decibel, that is dB. Correct? You might have learned somewhere in the electronic subjects where communication was coming in picture. Right? That means if this is, let us say you are having magnitude of GHJ omega as m. Correct? So what we are supposed to do, while putting on the plotting, we are going to take log of m to the base 10. Correct? And you are going to multiply it by 20. You are not just taking log and finish. No, it's not that, right? You are doing this thing. You are taking log of this thing. Means actually you are multiplying it by 20 and to the base 10 you are taking this, and this will have unit, that is decibel. Now you may say log was sufficient. What is the need to multiply it by 20? And one more thing, what is the need to take to the base 10? You may have e or any other base also will do the work, right? Work for us. Why we are following decibel? Because Bode followed the thing. Why he followed? Because this is very well known unit for which is a while taking log, right? For sound waves, right? And for communication engineering, this is a well known unit. So he thought of following the same. Why to go for any other unit? So he followed decibel, and that's why, yes, definitely we are also supposed to follow the same. So then, yeah, why dB? Because dB is a well-known unit used in communication engineering, and this is a very old unit, and it's old one, and that's why you will find, yes, we are using decibel, which is followed by the by Bode, right? So the last point related to the basics, that is, now instead of writing this equation, how we should write? 20 log to the base 10 of GHJ omega is equal to 20 log to the base 10 of K plus 20 log to the base 10 under root omega square plus 1 minus 20 log to the base 10 for omega and minus 20 log to the base 10 for under root omega square plus 4. So keep in your mind, now onwards, whenever we want to find out the magnitude, yes, we are going to go for this. This is important for us. Yeah, clear, right? So this is the basics related with the Bode plot. Let me remove this paper first, and yeah. So on the next slide I'll put that, because this is the paper on which we are going to plot the Bode plot. Now why semi-log paper and all those things I am trying to tell you. Okay. So point A was the basics, point B will be the Bode plot. And of course again this is the basics of the Bode plot, right? Okay. So One thing is clear, we are going to have two plots. One is for the magnitude, another one will be for the angle. So now onwards we are not just drawing one single plot, we are drawing two plots. So on this line x-axis you are having omega, this is also omega, right? Then you are going to have this thing is called as magnitude plot, and this is called as angle plot. So how both these things separately varying with omega we are interested in, correct? So two different plots you are going to have. On the y-axis you are going to have gain, yes of course, and it is going to be in dB, right? Then the second thing is this axis will be angle, will be in degree. Normally we will denote it by phi, right? So this is for angle and the magnitude and the angle plot which are going to be there in Bode plot. Now one thing is one more thing you keep in your mind, this x-axis, right, is not just omega, this is going to be log of omega. Now why log of omega? Because you very well know that if we'll have this thing in log, we can have more frequency range that will be fitted on this plot. So I'll write this is a log scale. This is also log scale. So I'll add that point over here, point number 1. X-axis is log scale, and so it is going to be log of omega. And what is the reason for that? More frequency range can be handled. Correct? Then the second thing is, keep in your mind, this thing is dB, this is not a log scale. Already we have calculated the magnitude in dB and we are going to put the values. So definitely this is going to be a linear scale. And here we are just putting the angles, definitely it has to be linear scale. After taking the log of magnitude, actually we made it linear, correct? No, previously it was not linear, we took log for that, and because of that it became linear. Then one more question may arise in your mind, if we have to take log, right, instead of having just log scale, you may have log scale over here also, and you can have log paper. Right, but we are not going to use log paper, we are going to use only semi-log paper. This is linear, this is log scale, so we are using semi-log paper. And the reason is, see, both the things we want to put on a single plot. This is linear, this is log scale, this is log and log scale. You cannot fit on the single paper because this will be log paper, this will be semi-log paper. So you cannot have both the things on the same paper, correct? And that's why you will find, yes, we are using semi-log paper as angle plot is already linear one. And therefore not using log paper, log paper, but we are going to use the semi-log paper, correct? So this is the reason why we are going for semi-log paper. So for this thing, you are going to take the magnitude in log and going to put it over here. Phi, so definitely you have to put it directly on the paper, and done for that, right? Yeah, so then talking about the semi-log paper, already I have told you that yes, vertical axis is going to be linear, horizontal axis will be a log scale. Vertical axis take log and then put on the graph. Horizontal axis no need to take the log because paper is doing for you, and that's why it is linear log paper. So I'll mention over here, semi-log paper is linear log paper. Log is not there for both the axes, that's why it is semi log paper, right? Then the next thing is why we are going for horizontal axis as omega, right? Log of omega. So I'll draw it and I'll explain. Fifth point, that is your horizontal axis. I've mentioned over here, more frequency range you can handle means what I would like to tell you. Horizontal axis, and why you want log on the horizontal axis. Let me draw the thing. See, when you are having this and you know that log, whenever you are talking about, you are taking log, that means what is going to happen? It will be 10 raised to 0, 10 raised to minus 1, 10 raised to minus 2 on this side. On this side you are going to have 10 raised to 1, 10 raised to 2, 10 raised to 3. Correct? So never you are going to get 0. Your origin will be never at 0. So where you fix your y-axis will depend. Right, depend upon the frequency range in which your system is going to work. Right, so this thing, this portion, right, this will be your performance frequency, because you know that yes, most of the control systems you will find, yes, they are working on low frequency range. The input is not changing with very high frequency. So I'll write for performance frequency. So if you want to see how your system is varying with respect to the input, that is given, this area will be important for us, and definitely because it is on lower range, you will find it is expanded one. Then you may think of what is the need, only will consider this range, no, if it is having lower frequency. But on this side you will find, yes, we are going for higher frequency, and those are important for considering the noise or studying the effect of noise on your system. Correct? And even if this is compressed area, no problem. We just want to see the effect. We are not detailing this area, right? What is the effect of noise on the frequency we are interested in? And that's why here it is low frequency, and on this side you are going to have high frequency. Low frequency will, should I write frequency? Yeah. So lower frequency will give you the performance of your system, and higher frequency will talk about what are the characteristics of the system. Okay. Yeah. So I'll save this. So I'm going for the building blocks now. Now actually we are starting with the Bode plot, not with the example, but with the basic things related to the Bode plot. And I'll say point number C. That is basic building blocks. Now when you are talking about basic building blocks, right, you will find that yes, your transfer function OLTF may have gain K, may have pole in the origin, 0 at the origin. You may have 0 at the pole at the origin. You may have a real 0. You may have a real pole, or you may have some complex one, complex zeros and complex poles. So except this, nothing is going to be there in your system, right? So we'll consider these as single blocks. We'll try to find out what are their individual graphs are, right? After taking log, definitely you are supposed to add them or subtract them. So you will put all these things on the plot, you will add or subtract, and you can have graph of the OLTF. And this is the basic idea behind the Bode plot, right? Yeah. So what can be the basic blocks? I'm just summarizing the thing. Number one, you may have constant gain K. Okay. Second thing, you may have a pole at origin or 0 at origin. I'll put it as same. I mean in the single point at origin. Third thing, you may have real pole or real 0. So I'll write single real pole. And definitely, even if it is multiple, what you have to do, you have to go separately for each as per the thing that will specify over here, and then again you are supposed to add. Or you may have single real 0. And the fourth thing is, yes, you are having complex poles or complex zeros. You should not write complex pole because single is not possible. That's why complex poles or complex zeros. So now what we are going to do, we'll go one by one for the individual one, correct? And we'll try to see what will be the Bode plot for those components, correct? Yeah. So we are going for first one, and that is constant gain K. Yes, let me make a partition. Correct. Now constant gain K, if you are saying, let us say K, your transfer function is a gain, just a number, GH of S is equal to K. And you know that, yes, we are in frequency domain, so we are supposed to write GH J omega, no change on K because it's just a number, it will be just K, correct? So if you are talking about gain over here, that is magnitude of GH J omega, very much clear over here, very simple, that is just K, correct? And if you are having phase, yes, now if this is positive, what is going to happen? And if this thing is negative before taking the mod, right, you may have this K to be negative. In that case, what you are supposed to do, I'll tell you. Phase, that means you are talking about angle of GH J omega, correct? Now this angle, if I'm saying phi, correct, this phi will be equal to 0 if this K is greater than 0, that means it is positive, right? On the same line, if this will be negative, that means K is less than 0, then this angle will be minus 180 because it will be on the real axis and negative real axis, and that's why you will find it is minus 180. Now if I want to draw it on the W plane, how it will look? I'll write it over here that this is W plane. Now no need me to tell you because 100 times we did this thing in Nyquist plot. This is your real GH J omega, and this is your imaginary GH J omega. Fine. When the gain is positive, that means from this point, let us say till this point it is okay. Over here, just a minute, this is your K is equal to or I'll write K greater than 0, and that's why you will be able to see yes, phi is 0 degree. On the same line, if it is on the k is negative, that means on this side, that is k, this point k less than 0, then in that case your phi is going to be minus 180 degrees. I'm very much clear over here. Angle is minus 180, correct? Now what will be the Bode plot for this? Yes, I would like to show you. Just give me 1 sec. Yeah. So this is a semi-log paper. You might have used it, correct? Yeah. So this is a semi-log paper. Now we want to put all these things over here on the plot. Alright. You can see semi-log paper means what? Let me explain you that thing first. Let us say I'm going to plot magnitude over here, and let us say angle I'm plotting over here. Now how much scale and what scale you are going to decide, that is up to you, alright? But these lines I will explain you. Yeah. So what I'm talking about? I'm talking about this is magnitude plot, and this is, I'll write it over here, angle plot, right? This gain will be in dB. This is in degree, or I'll write phase, that is phi. This is your phi, correct? This is gain in dB. So now see, whatever scale that you want to use it over here, one unit means what, 2 dB, 3 dB, 4 dB, that is up to you. But I'm just bothered about linear scale के लिए आपको कुछ doubt नहीं होना चाहिए. For this line, yes, you can see, yes, already log is there. This is showing you the frequency, right? And already you are going to get log of that is log of omega actually over here. So if I am marking omega equal to 0, let us say over here, omega 10 raised to 0, then it will be 1, 2, 3, 4, 5, 6, 10, that means 10 raised to 1, then 10, 20, 30, 40, 100, 10 raised to 2, and will be continued, right? On this side, yes, it will be 10 raised to minus 1. 10 raised to minus 1 means 0.1. Then 10 raised to minus 2. That is 0.01, right? And will continue. Never you are going to get 0. Now, where to fix this axis depends upon your system. कि आपके system का frequency normally क्या होता है? ठीक है? So it depends upon the cutoff frequency of your system, or it is also called as breakdown frequency. So breakdown frequency or cutoff frequency tells you that yes, after this frequency the system gain will be very less. So definitely you are not going to allow any of the frequency, right, from input side to your system. You know that for this frequency my system is not going to work, so no need to use that frequency for my system, correct? So whatever will be the perfect area for your frequency, for your system, your area of the frequency rather, right? You are going to select that much range of the frequency for your system. That is also called as bandwidth. तो वो bandwidth क्या होता है और cutoff frequency, what all those things are, we'll see. Have patience, right? In the next lecture, I'll explain you all these things. Okay. So what I'm saying is, over here, now you got 20, but when you want to put it on the plot, right, what you should do, gain in dB. If you want to have gain in dB, what you are supposed to do, 20 log of k to the base 10. So whatever is this value, you just put it over here and get the value. Because your k is constant, this value will be also constant. So no need to worry, it will be just a straight line. Let us say this is the straight line. For that, the one thing is getting cleared in our mind. Whenever gain will be there, the line, the plotting will be parallel with the x-axis. No slope will be there for the line, right? For gain only I am talking about the gain, right? And this point will give you it is going to be, not will give you, it is 20 log 65 20 log to the base 10 k, correct? And on the same line, now we have not found out the we have found out the angle rather, right? So phi equal to 0 or phi is equal to 180. So let us say this is 0 degree. 1 2 3 4 5 divisions will say it is equivalent to 90. So 90 degrees. Then 1 2 3 4 5, that means this is going to be minus 180 degrees. Definitely if you are getting some positive values, will go in the first and second quadrant, right? So phi is 0, so I am going to have a straight line over here. Yeah, I'll draw that line. So from this, on this line you are going to have k. This line is for k greater than 0. Phase plot, this will be the phase plot, right? And second thing, yes, you are going to have minus 180. So this line will be for k less than 0. So this is the, for constant gain k, these were the plot absolutely parallel to the x-axis, correct? Now what it is for the if you are having any pole or 0 on the system, let us see. We'll go for the second one now, pole at the origin. If you'll understand pole at the origin, will be very simple for you to understand. For if you are having a 0 at origin, what is going to happen, okay? So the second point, pole at origin. Now when pole is at the origin, you know that GH of S, you are going to have in the denominator one S term. One by S. Now if it is 1 by S, and if you are talking about the frequency domain, actually you should write 1 upon j omega. So I'll write it. GH j omega is equal to 1 upon j omega. Now I would like to write it in the real part and imaginary part separate, so will be easy for us to go for. So I'll multiply and divide by j. So j square minus 1, it will be minus j upon omega. So I can write this, I can say 0 plus j minus 1 upon omega. I think all of you agree with me, correct? So if I am talking about gain for this, that is magnitude of GH j omega, then it is going to be 1 upon omega, correct? Angle, when you are saying phase, I'll write, instead of saying angle, phase, that you denote it by angle of GH j omega, right? This angle is going to be tan inverse of this upon this. Just a minute. Correct? So tan inverse of minus 1 upon j omega divided by 0. So it is going to be tan inverse of minus infinity, and tan inverse of minus infinity will be minus 90 degrees. So our interest is on these two things. So if I'll draw that thing, just a minute. Yeah, see, again what I'm trying to draw on the W plane. On W plane, I'll write magnitude is minus 1 upon omega, correct? Minus hai, so definitely, but the angle is telling you it is minus 90, so definitely it is in the downward direction. So I'll draw it from this point in this direction, and you are going to have this magnitude to be equal to 1 upon omega, right? And this angle definitely is minus 90 degrees. Is it okay? Right? Now the next thing we want to know, for different frequencies what is going to happen. So we should have a table where it is telling you all these quantities. So let me draw the table. And for at least 4 or 5 frequencies we'll try to write it, so will be easy for us to understand what is happening. Yeah, so the first block is of omega, different frequencies you are changing. As per that, what is going to happen to gain K, which is 1 upon omega. Then what will happen to gain in dB? Correct? And this is for the phase or the angle that you are having. Right? So we'll start with 10 raised to 2, say we'll start 10 raised to 2, 10 raised to 1, 10 raised to 0, 10 raised to minus 1, and 10 raised to minus 2, more than sufficient, 4 5 values, correct? Now when this omega is 10 raised to 2, this is in the denominator, that means it will be 10 raised to minus 2, 10 raised to minus 1, 10, correct? Actually it will be 1, correct? 10 raised to 1 and 10 raised to 2, correct? Now gain of this in dB. Now gain of this in dB means I'll write it over here, 20 log to the base 10 of this K, whatever gain that you are getting, correct? So 20 log of 10, 10 raised to minus 2. So 10 raised to minus 2, minus 2 going over here, it is going to be minus 40 dB. 10 raised to minus 1, minus 20 dB. 10 raised to 1, right? 10 raised to 1 means it is going to be 0. Just 1, right? Just 1 over here. 10 raised to 1 means 1 on this side plus 20 dB. And this is going to be plus 40 dB. Okay, and angle is straightforward. It is nowhere omega is in picture, so for all the values it is going to be 90. No need to worry. Correct? So phase plot will be very simple. Gain plot, will see what is going to happen to that magnitude plot. So I'll draw it. एक ही एक्सिस ड्रॉ करते हैं, it will be fine, I think, correct? And this is telling you gain is in dB. Yes, so 1 2 3 4 5, let us say 20 dB. 1 2 3 4 5, so let us say 40 dB. 1 2 3 4 5 minus 20, 1 2 3 4 5, so minus 40 dB. Okay, and let us say this is 0 degree, 1 2 3 4 5, so I'll mark it minus 90. That this is more than sufficient. Again I'm writing, this is magnitude plot, and this is angle plot. I'll write it over here. Okay, let me mark, this is omega, this is also omega. Let us say this is 10 raised to 0, 10 raised to minus 1, 10 raised to minus 2, 10 raised to plus 1, 10 raised to plus 2. Sufficient hai na? These many frequencies we had taken, so it's okay. So at 10 is equal to 10 raised to 0, I'll write it again. This frequency, what you got, magnitude to be 0. So yes, this point is there on the line, correct? Then at 10 raised to minus 1, it is plus 20. That means over here, this point. For 10 raised to minus 2, 10 raised to minus 2, it is 40 dB. This point. Then 10 raised to 1 minus 20 dB. And minus 40 dB. And very well you can understand from the plot that it's just a straight line. Yeah. Still it is now it is 20 dB. Now just see what is the slope. Slope is, it is decreasing slope, right? So minus 20 dB ka slope it is there, and per decade. Now what is the meaning of decade? Multiplication by 10. This is getting multiplied by 10, you are going over here. This is getting multiplied by 10, you are going over here. So this one span is a decade, and for every decade it is getting decreased by minus 20. Why minus? Because it is decreasing, and very well it is understood. 40 say 20, 20 say 0, 0 to minus 20. So the slope that you are having over here for this line is minus 20 per decade, correct? And if you talk about the angle, very well clear, it is just minus 90 ka straight line. So what I want to tell you now, yes, whenever you are talking about a pole at origin, you will find that you are going to, so one thing is fixed, pole at origin. I'll write single pole. Why? Because single pole is more important, right? So I'll write single pole at origin. What we got is a line with slope minus 20 dB per decade. Right? Now if you'll have two poles at the origin, now you just see you are having 1 upon s square, correct? So square, and square means multiplication mein the power will get added up, and then you will find that you are going to get a line. Abhi now I'll not do this thing. I have already shown this thing in the notes. So all calculations I have given you over there, right? I want you to search for it, see in the notes and see what you are getting. Now I am directly telling you, you are going to get a line with slope minus 40 dB per decade. and in that case the angle that you are getting, you will get it to be equal to minus 180. So I'll write phi minus 180. आप करके देखो, you just see the notes, you will find the same thing, right? So I'll try to draw the thing. So for two frequencies, now you will find at this point, actually this point you are getting over here, and will pass through the origin definitely, and again over here you will get the thing. So if I'll try to draw the line going through these points, yes, so this is for 1 by s and this is for 1 by s square, two poles at origin, and the slope is minus 40 dB per decade. ठीक है, and if I want to draw the phase 1 2 3 4 5, so minus 180. Okay, and you will have line the phase plot over here. So is it possible for me to shift this? Yeah, I'll shift it over here, and this thing is for 1 by s square, and this is for 1 by s. Right, so I think I have tried to complete two components. Remaining components will complete in the next lecture.